Hello, everyone, and thank you for joining DataCon LA 2020. Welcome to the AI ML Data Science track, and soon we'll be listening to Gradient Boosting Machines from Zero to Hero session with Szilard Pafka. I am Eli Selkin, your host, and our co-host today is Aaron Artea. We will be moderating the chat and Q&A for you during this session. Today, we have as our guest Szilard Pafka, and he will be talking about gradient boosting machines from Zero to Hero. Szilard studied physics in the 90s and obtained a PhD by using statistical methods to analyze the risk of financial portfolios. He worked in finance, then more than a decade ago moved to become chief scientist of a tech company in Santa Monica doing everything data. He is the founder organizer of several meetups in Los Angeles area and the data science community website, datascience.la. He is the author of a well-known machine learning benchmark on GitHub, more than 1,000 stars, a frequent speaker at conferences, and he has developed and taught graduate data science and machine learning courses as a visiting professor at 2 universities. Without further ado, I'll hand over to the speaker, Szilard Pafka again, and thanks for being here.
Thank you so much for having me at DataCon LA 2020. And thank you, Eli and Aaron, for hosting me. And also thank you for this great introduction. So I can, you guys can see my slides, right?
Yes.
All right, so I can skip the intro slide. And then just a quick disclaimer that nothing I say here has anything to do with my employer, of course. And as you know from the title of the talk, I'm not here to talk about deep learning. So despite that deep learning is the buzz, it's been in the media for the past 3-4 years. And there are awesome claims that like deep learning is the best, it's beating everything else, all the other previous machine algorithms can go in the trash bin. And it's beating humans, and we'll have soon self-driving cars, and we'll have AI and whatnot. So I think a lot of this is bullshit, and I'm here to clarify some of the things around this. And I have to start with actually deep learning. It's really great for images, for computer vision, and also it had some success in predicting sequences like text and NLP. And indeed, I fully acknowledge that in virtual environments like games where you can create as much data as you want and you can combine it with reinforcement learning, deep learning had really tremendous success. However, real life is a little bit different, especially if you're working in businesses and business problems. And also, I'm not really sure if deep learning is gonna solve AI. On the other hand, we have had machine learning in businesses for 30, 40 years on many areas. Fraud is one of the areas I'm working on, but also in like credit scoring, marketing analytics, manufacturing, insurance, telecoms. You have all these businesses that have been using machine learning for like 20, 30, even 40 years. And I was wondering if deep learning can beat some of this machine learning algorithm that we have used in businesses on some of these business problems. So in businesses, we have mostly structured data sitting in databases, in relational databases. And then we need to predict something. And often this data sets are like a mix of categorical variables and numeric variables. So I had looked at many of these data sets and also some of them public. So here is something I did in 2015. I tried to beat random forest and gradient boosting machines on this airline data set. So here you need to predict if a flight will be delayed or not. And then I tried many architectures. I talked to deep learning experts. Uh, they try to help me to build various neural network architectures that could match the accuracy of random forest gradient boosting, and we couldn't really come even close. So deep learning is not really the best for everything. So especially on this structured tabular data that one finds very often in business problems, in business prediction problems, deep learning is not probably not the best. And here's a little bit later at the LA meetup, Tianqi Chen, who is the author of XGBoost, which is the most popular gradient boosting library. And he's also the author of MXNet, which is a popular deep learning library. So he knows both sides. And he was talking about that 2/3 of Kaggles in 2015 were won by gradient boosting and not deep learning. Basically, the problems that had the structured data, this kind of business prediction problems, were more like gradient boosting, and then the image, text, and speech recognition problems were won in Kaggle by deep learning. So here's kind of my version of the slide that I showed at the beginning. So I don't think deep learning is the best. Actually, in typical business prediction problems, deep learning is almost not always the best. So usually gradient boosting can beat deep learning on this kind of problems. And then later, uh, I've seen talks from Anthony Goldblum, who is the CEO of Kaggle. He was kind of saying the same. But a more honest answer is it depends. So it really depends on your problem and your data. And then I don't say don't use deep learning. I say I encourage you to use various machine learning methods and try them all on your data and then see what works best. So the media portrays machine learning as something like this. I don't think it's this. I think it's more like this, where you have some data and then supervised learning is about fitting a function that will predict new instances. And then we need to learn or fit this function to the data. And this function can be something simple like linear or something more complicated like a nearest neighbor, or it can be like a neural net or something even more complex. So in this talk, in the abstract of this talk, I kind of advertise that you can listen to this talk and get started with gradient boosting without having too much machine learning background. That's a little bit of a lie. So I really want people who use machine learning to have at least some basic understanding of the basic concepts. And here is just like a reference slide. Uh, what I think is kind of a must to know before you get into doing machine learning, because otherwise you can just shoot yourself in the foot. So just like statistics, it's a lot of pitfalls, and then you can do really stupid things if you don't know what you're doing. So here are some books, but maybe these are a little bit more advanced. If you want some kind of quick route to basic machine learning concepts, then there are a few Coursera courses. If you just Google for machine learning Coursera, you will find them. To get you to up to speed so that you kind of know what you're doing. And ultimately, all is this machine learning is kind of like a part of data science or data analysis, with other parts being like exploring data and cleaning, transforming the data, and all the other parts that we need to do in a data project. Okay, let's get started with gradient boosting. So boosting is based on trees, decision trees. Decision trees are learned from the data. Probably most of you have heard of decision trees. So um, there are various algorithms that you can learn the structure, the splits, and splitting points, and so the leaves will. So this So basically, a decision tree splits the instances in your data based on variables, which like you can go left or right depending if that variable is greater or smaller than a given threshold. And then all this is learned from the data. So the splits, the variables, and the leaves, which is the contains the predictions. And this is the building block for gradient boosting. So the first boosting algorithm was AdaBoost, and you don't need to understand the formula. The point is that you fit decision trees sequentially, and each tree is trying to correct the errors that the average of the previous ones are making. And you do this by upweighting the instances that were wrongly classified by the previous trees. So you don't really need, if you want to understand more about gradient boosting, you can look at this. But for now, this is gonna be enough. And then gradient boosting is doing something similar with a gradient. So again, uh, later you can look at that and understand what's going on, but you don't really need very much in-depth understanding of this. Just that there are trees, we fit in sequence trees, and then each tree is trying to correct in some way the errors that the other trees are making. And then at the end, we'll take some kind of weighted average of the prediction of all the trees. So what can you use? What software can you use to do gradient boosting, machine learning? Here are some of them, and I did a benchmark. I started in 2015 with this first repo, and then in 2017 I focused on GBM only. And the gist of this is that the best open source implementations are xgboost, H2O, and later lightgbm. And you can use either of them from R or Python, and I will have some demo later on in the talk. You will ask me, but what if I have big data? No, you probably don't. There are surveys that show that most people data fit in the RAM of one server. You might have like tens of millions of records, but that's still not big data. And even if you have big data, big raw data, when you do machine learning, you need to aggregate it and refine it. You don't do machine learning on clicks, you probably do it on users. So there are much less users than clicks. You already have some kind of aggregated data that most likely is going to fit in the RAM of one server. Just get more RAM. You can get it on the cloud. Uh, and what about Spark? So unfortunately, Spark is really bad at gradient boosting. So it's like 100 times slower, and it's using a lot of RAM, and it will crash. So just forget about Spark. Don't waste your time with it. So the best ones are, as I said, H2 XGBoost, lightgbm. Later, xgboost is also a newer library, is also catching up. So I have here some benchmarks, and I will give you references later on to some other talks where I go more in details. But if you are looking for the fastest training, then lightgbm is probably the fastest on CPU. And if you have a GPU, some of those libraries have GPU implementations. XGBoost, I think, is currently the best one, fastest and the most stable. But if you want to run your machine learning thing in production, then I really like H2O because it makes it much easier than the other ones to deploy your model as a REST API web service. So all you need to do is what's included in this slide. And then you will have up and running Java service that will serve you. You can make requests over HTTP and then get scores. Here's some kind of quick comparison of these libraries. So I think the gist is that if you want fastest training, then and you don't have a GPU, the XGBoost, lightgbm. If you have a GPU, then XGBoost. If you care about productionizing your models, then probably H2O. But there is a lot of more into this, so it kind of depends. The most honest answer is it depends. It depends on your project and data and what you want to do. I think by now people have figured out that those are the three best libraries. So I did surveys, and those are the ones that come on top. And if you ask me about Spark, not many people are using it. And then this is a more recent one. The other survey was a year ago. This one was a few weeks ago. So you can see that it's kind of the same order. All right. Let's get into the demo, and you can find all the demo code and this GitHub repo. And I also put screenshots in the slides because I gave this talk in LA at the meetup, the last in-person meetup in February, but we'll not need that. So now I'm gonna stop the share and share my screen so that we can start the demo. Oh, I'm not sure if, can you guys see now my RStudio?
Yep.
All right. And so installing xgboost is very easy. So we'll do the demo in R and Python. Installing xgboost is on CRAN, very easy to install. H2O needs Java, but it's also on CRAN, easy to install. Lightgbm is not yet on CRAN. It's a little bit more involved to install, but you can find the installation instruction if you just Google for lightgbm install R. In Python, it's easy to install all of them with either with pip or with conda. We can jump into using them. So I'm gonna use the same airline data set that I was talking about. This is in R first. So the data looks like this. So basically, here are some inputs like month, day of the month, and we are trying to predict if the airline, the flight was delayed by more than 15 minutes. So XGBoost requires you to do some kind of encoding of categorical variables, so it cannot deal directly with categorical variables. I'm using this one-hot encoding, and I really suggest someone who is doing one-hot encoding, they should use parse matrices because they use much less RAM and they also make training faster. So they will look like this. So one-hot encoding is encoding the categorical variables into 0 ones, and the sparse matrix representation will store the ones and not the zeros. Then what you need to use XGBoost is to build this D matrix, which is just copying your data into a highly optimized matrix format that XGBoost is using. And then you can start training. So training with XGBoost is very easy. It's one line of code. You just have to specify the data. This is a binary classification. Then you will specify how many trees you want. We were talking about that gradient boosting is building trees. Then you have to specify the maximum depth of these trees. And then there is a learning rate, which is used in combining these trees. So I can run this. It's gonna run 100,000 records. That's the input data. And I'm running it on a small laptop. So it ran in 4 seconds. You can display some statistics about the model. And then you can start predicting. So we're gonna predict on new data. And all you need to do, again, one line of code, and then you get predictions. So you would see that predictions are the likelihood that the flight was delayed or not. So this goes from 0 to 1, and here is some statistics. So we can also create a confusion matrix. So here is what we predicted, will be the flight be delayed, yes or no, versus what was truly happening in the test data, yes or no. So you can see that those are the flights that were not delayed and were predicted as not delayed. Those are the delayed and were predicted as delay, and those are the errors. There is also in classification, people are using this ROC curve, which shows the trade-off of false positives versus true positives. And also you can calculate the area under the curve, which would be some kind of metric for the goodness of the prediction. So 0, 5 would be a random prediction, 1 would be a perfect prediction, and we got here 0, 73. And then you can use different threshold and get different confusion tables. And that's pretty much to it. So basically, to recap, all we did is reading some data, very easy in R. We needed to do this one-hot encoding for XGBoost, and then copying the data into a format that can be used in an optimal way to do gradient boosting. And then training was kind of one line of code or counted as two. And then predicting was one line of code. So basically, all it is to gradient boosting is that one line of code training the model, one line of code predicting using the model. So very easy. Now let's do the same in Python. I'm gonna change the screen, share to this one. Can you guys see an IPython command line kind of screen?
Yes.
Okay, great. And now I'm just gonna use a very similar node to a very similar code to the R code. So you see it's the same data. We read it from a CSV file. And then in pandas, I also do this one-hot encoding. In Python, these sparse matrices are not as well known, but you should use sparse matrices as well because it's I tested is much faster and uses less RAM. So what you need in Python is to import for SciPy the sparse matrices, and then just use the auto encoder, the one-hot encoder, and then when you concatenate the matrix with another one, use this sparse A stack. And at the end, also transform it back to this CS. The CSR is a sparse matrix representation. It really makes your code faster. The training will be much faster, like sometimes 10 times faster if you have larger data sets. And then there are two APIs. One is scikit-learn star API, which is this. So you can see the number of trees 100, the depth of the tree 10, and the learning rate the same. And then basically xgboost is C++, so the same code runs from R or Python. And then we can calculate score here. So this was training, and this is scoring or prediction, and we have an AUC. And then there is also a classical API in which we do by manually this D matrix. In the scikit-learn or API, this D matrix was created under the hood. And then here we can also predict. So basically in Python 2 is one line of code training the model, one line of code making predictions. That's pretty much. And then you can play with this hyperparameters. So let's go back to our So I'm back to the R Studio. If you want to use GPUs, it's very easy. If you have GPU, you just need to install xgboost with GPU. And the only thing you need to change is here the tree method, when you grow the tree being GPU hist, and then it's gonna use the GPU. Depending on the data, your data is gonna be faster or not. So like GBM is very similar. We use the same data, and then it has another format, and then also here like one line of code training, and then here it doesn't specify the depth of the tree, but how many leaves you're gonna have, and then you can make predictions, and then you can also calculate the AUC. It's gonna be similar 0.73. And finally, H2O. This is, you're gonna start the Java process, and the R or the Python client will connect to this Java process. You're gonna upload your data to this Java server, and then you're gonna train one line of code. Again, the same number of trees, max depth, and learning rate, and then you're gonna score and compute AUC. So as you see, H2O is a little bit slower, especially on smaller data. And this was 100,000 records on a laptop. So if you have millions or tens of millions or even hundreds of millions, it's still gonna work on a server. You just need a little bit more RAM maybe. And you have more cores too. All right, let's go back to the slides. Uh, I'm not sure where's the, yeah, 1 second. I think I closed the full. Can you guys see the slides? No, this is not the slides. Oops. Sorry. Okay. One sec. All right, here's the slides. So this is recorded, so it doesn't matter. This doesn't help too much to have here the screenshots from the demo. And then for now, we can almost close. So I think that if you have tabular data, you absolutely must use GBMs. Usually it's the best. That gives you the best accuracy. It beats deep learning on this kind of business structured data, tabular data predictions. If you want to go beyond this talk, then I have a lot of GitHub repos. And here are some of them. And then if you don't like to read too much, then you can listen or watch some of my other talks on YouTube. Here's one that's more advanced. It goes more into details of how of the benchmarks and how these libraries work and how to use them a little bit more. But the most advanced talk I ever given is the one that's coming now at the LA Data Science Meetup on November 10th. So you can still sign up to this one. It's going to be online on Zoom. And it's going to be actually 2 talks. So I will talk about the benchmarks more in depth than in any other talk before. And we also have the main maintainer of xgboost, who is now living in LA, and he's going to give us a talk about the state of xgboost. So sign up RSVP at the meetup if you are interested. It's November 10th. So with this, I kind of finished just in time, and we'll have 10 minutes for questions. You can ask them on chat, and then the moderators will read them to me, and then I will answer. But if you don't get a chance to ask a question, you can also contact me later on any of those channels. So thank you so much for this great opportunity to talk at DataCon LA.
Thank you, Szilárd. So we have one question already. And the question comes from Li Shuangshen. How do you think about the risk of overfitting in GBM and XGBoost? Advice on avoiding checking and reducing overfitting. Thanks.
Yeah, excellent question. So I was seeing I was a little bit late, so I kind of skipped like 2 or 3 minutes about early stopping. That's the best way to, but I actually have it here in the slides. So there is some, so if you train for too long, neural nets or gradient boosting is gonna start overfitting. So basically you have to look on a separate validation data set at the accuracy, let's say AUC for classification, for example, and you would see that if you train more and more, the accuracy on the training set will go still up, but that you would fool yourself. On the separate validation set is gonna start to go down. And basically that's when you want to stop training. So all these libraries, XGBoost, lightgbm, H2O, they have a very simple way to do early stopping. All you have to provide is those parameters like early stopping rounds, and you have to provide like a separate validation set from the train, a separate set from the training set that it will check the accuracy, and then it will stop once it's gonna see that the accuracy is going down. So this is how you can that's kind of the default way to prevent overfitting for GBM. But also you can also, if you know that I mean, when you train GBMs, they have a lot of parameters, so there is a lot of tuning that might be involved. Some people are tuning by hand, or they're using random search or grid search or some Bayesian method. So you have to also be careful not to, let's say, not use too deep trees. So if you know that you don't have a lot of data, you don't want to overfit, then try to restrict the number of trees. That's another way you can uh, restrict overfitting. And there are many other parameters. There are some L1 and L2 regularization, for example, in XGBoost and lightgbm, you can use those. So there are, so Google for, actually, I have it here in the slides. So these are two blog posts about tuning. It's kind of involved, and then they will give you some ideas of which parameters to kind of restrict so that you don't overfit.
Thank you. Let's see. We're open for questions, so if anyone wants to type a question, they most certainly can right now. Okay, so Li Shuangshen had a follow-up. He said his typical data set is 100,000 rows, 200 columns for 5-class prediction. I often get AUC of greater than 0.98 in training validation, kind of feeling too good to be true.
Yeah, it might be. I mean, it depends on the problem. So in some problems like finance, you're lucky to get just a bit 0.5. In some others, I think this 0.8 is a lot. It's very typical on business problems like uh, 0.85, 0.90. Yeah, on some problems where, I mean, it's either one or two variables, they are very predictive, or the whole thing is it's very easy to detect. Yeah, I had projects where I had 0.98 and it was all good. So another thing I can say about textbooks machine learning versus machine learning in practice. So what you have to be careful is how you split your, let's say, train test set or train validation test set. Is in practice, a lot of times it's not really a good idea to do cross validation by mixing. You have to be cognizant of time. So you have to kind of split a train test, for example, so that every instance in the test set is in the future time of the train test, so that when you train, let's say you train on January to August data, and then you predict on September and October data, and not like do folds and then you kind of mix the data in time. Because sometimes also let's say you train on, I don't know, 6-9 months of data and you get a great AUC, but on the next month of data, your model will uh, be much less predictive because, let's say, in your problem, distributions change slowly in time. In that case, you will see a decrease in AU accuracy. But in some other problems, it might even change more. So you you really have to consider, and this is not really taught in like machine learning textbooks. It's something like people pick up by themselves in practice, and I didn't see. I mean, I see it a little bit more now later, blog post and a little bit more talk about this. But like many years ago, I kind of invented that by myself. But obviously, many others have done the same. So, and indeed, and the other thing is you need to do also when you deploy your model in production, you need to do also online validation. Like you validate on a test set when you develop your model and before you deploy, but then deploy it and then also validate it, the deployed model on the prediction that's doing in real time. And because that can be different for one reason is often because of some bug, and then it's good for debugging. And the other reason is because of this kind of slowly changing distributions, and also the model will get degraded. But to answer the question, if you find the same AUC or very, very high AUC uh, with a proper time split and also with in production with online validation, then everything should be good. I think just should be happy.
I'm gonna have to stop us there. Thank you, Szilard, for your presentation, and I appreciate all the attendees for the questions and interactions during the session. Please contact the speaker if you have further questions regarding this topic. Please provide your comments and feedback to us or the organizers on the community board, or start a discussion there to connect with others in the DataCon LA 2020 community. Thank you for joining today's presentation, and I hope you have gained some insights from this session. Have a wonderful day, and thank you for being a part of this year's DataCon LA. Thank you again, Szilard.
Thank you, Eli, and thank you all the DataCon LA team. Thanks for having me.
Great.